Hi everyone, I'm Chang Lu from Stevens Institute of Technology. Today I'm going to present our work, Collaborative Graph Learning with Auxiliary Text for Temporal Event Prediction in Healthcare. My collaborators include Professor Reddy from Virginia Tech, Dr. Chakraborty from IBM Research, Professor Klingberg and Ning from Stevens Institute of Technology. Here is the outline for this report. I will first introduce some preliminary about health event predictions, then I'm going to talk about our work named CGL. Finally, I will present experiments to demonstrate prediction performance and analysis to the results of our method. In modern healthcare systems, electronic health records data are widely used for recording patients' visit information to hospitals, such as diagnosis, procedures, medications, and clinical notes. EHR data are able to automate access to information and have the potential to streamline the clinician's workflow. In addition, they also provide valuable resources for researchers. Here are some examples of EHR data. Patients and visits are encoded into ID, and patients can have multiple visits to hospitals. To better classify diseases, the ICD system is designed by the World Health Organization. In the ICD system, diagnoses and procedures are assigned with digital codes. They normally form a hierarchical structure. This figure shows an example of this hierarchical structure. The higher level diseases provide a general description to a category of diseases. The lower level diseases are more precise to describe the disease with details. Traditional prediction models in healthcare such as Graham and Gilbert explore the disease hierarchical structure with attention methods. It is able to detect the ancestor-children relationship. However, except the ancestor-children relationship, there are another relationship among diseases represented by lymph nodes. Although two diseases do not belong to the same parent, they may frequently co-occur in a number of patients' diagnoses. This relationship can reflect disease complications and help to predict future diagnoses. Therefore, we want to detect this kind of horizontal relationship for diseases. Another challenge is how to collaboratively learn patient-disease interactions. In existing work, patients are regarded as independent samples. If we want to predict future diagnosis for a patient, existing work only uses previous diagnosis of this patient to make predictions. However, this kind of method ignores the patient-disease interactions and patient similarity. For example, in the right figure, patient 1 and patient 2 are similar patients because they have many common previous diagnoses. It is highly possible that patient 1 will be diagnosed an unseen disease but occurred in patient 2. In addition, unstructured text like a clinical note in EHR data also contain valuable information. Please see the following snippet of one clinical note. In this note, we can infer that this patient may have a history of respiratory problems and hypertension. Therefore, we also want to incorporate clinical notes to improve the prediction accuracy and interpretability. To address these challenges, we proposed CGL, a collaborative graph learning model with domain knowledge and auxiliary text. Here is the model overview of CGL. The first is learning domain knowledge with hierarchical embedding, and we create a collaborative graph for patients and diseases to learn the hidden relationship. Next, we use an RNN with attention method to learn temporal features for diagnosis. Finally, we propose a TF-IDF-rectified attention method for clinical notes. Here are the notations used in the CGL model, including the patient set U, medical code C, words in clinical notes omega and N. For the test visit, it includes a subset of C and N. For the hierarchical embedding method, the output is an embedding matrix for all medical codes E. Here key is the level number, and DC is the embedding size. For a leaf node, we concatenate embeddings of each level. Here we don't use a tension-based method because we don't focus on the ancestor-children relationship. If a patient is diagnosed with a higher level disease, the level number is different from other leaf nodes. In this case, we create virtual leaf nodes for these higher level nodes to make sure they are in the same level. Then we create a collaborative graph to explore the patient similarity and disease hidden relationship as mentioned before. The graph contains a patient disease observation graph and a disease ontology graph. For the patient disease observation graph, we create it based on the EHR data. The nodes are patients and medical codes. If a patient has been diagnosed with a medical code, we create an edge for them. This graph is represented by an adjacency matrix AUC. In this way, patients with similar diagnoses will have similar connections. For the disease ontology graph, we create it based on the ICD-9 structure. The nodes of this graph are medical codes. To model the horizontal relationship, we create weighted edges in this graph based on the lowest common ancestor of two medical codes. For example, the right two nodes are connected in a node in level 2, and the weight is 2. And the left two nodes are connected in a node in level 1, therefore the weight is 1. This graph can be represented by an adjacency matrix ACC. Then we use a graph neural network to learn a hidden relationship among patients and medical codes. The input of this graph neural network is a random initialized patient embedding matrix P, the medical code embedding matrix E, which is calculated by the hierarchical embedding, the two graphs AUC and ACC, and the graph layer number L. In addition, in the first layer of GNN, we use HP0 and HC0 to denote P and E. The output of this GNN is the final patient embedding matrix HP and the final medical code embedding matrix HC. In each graph layer, we first aggregate neighbors of patients in the observation graph. We use the adjacency matrix AUC to multiply medical code embedding HC and project to the dimension of patient with a weight WCU. Then we aggregate the neighbors of patients which are medical codes and get an intermediate variable ZP. Then we aggregate neighbors of medical codes in the ontology graph. We first define an ontology weight phi k for medical code CG to normalize the influence of CG on other medical codes connected in level k. Here μg and θg are two trainable variables for CG, and sigma is the sigmoid function. The second equation is for the matrix calculation using the adjacency matrix ACC, and we get an ontology weight matrix for all medical codes. And then we aggregate the neighbors of medical codes which are also medical codes by multiplying phi and HC. Finally, we use the transpose of the adjacency matrix AUC to multiply patient embedding HP and project to the dimension of medical codes with a weight WC. Then we aggregate the neighbors of medical codes which are patients and get an intermediate variable ZC for medical codes. In the next step, we use a dense layer with ReLU activation function and apply a batch normalization to calculate HP and HC in the next layer. In the last layer, we use HCl as the final medical code embedding HC and use HPL-1 as the final patient embedding, because in the following calculations for visits, we only use HC and HPL is not used. Then we use an RNN with attention method for temporal learning of visits. The inputs are visit sequences. They include the medical code record of a patient. Another input is the medical code embedding matrix HC calculated by graph learning. The output is an embedding vector OV for this patient. Firstly, we calculate an average of the embedding vectors of medical codes in each visit. Then we apply GRU to the visit embedding and use an attention method to calculate the weight of each visit. Finally, the embedding OV is the weighted sum of all visits. As we mentioned before, clinical notes also contain valuable information for predictions. Therefore, we want to highlight important words related to diagnosis in a clinical note. By introducing TF-IDF weight, we can provide better interpretability for attention weight. The input sample is a note in the last visit. We think that it contains the medical history and future plan for visits. Firstly, we calculate a TF-IDF weight beta for each word in the note. Then we calculate attention weight alpha for each word using word embeddings and visit output OV as context. Finally, we designed the following penalty function to let TF-IDF weights guide the attention weight so that important words can be simultaneously detected by TF-IDF weight and attention method. After calculating the output OV for the medical codes and output ON for clinical notes, the model output O is the concatenation of them. Finally, we use the combination of TF-IDF-rectified attention loss and cross-entropy loss to train the model. Here, lambda is a coefficient to adjust the weight of attention loss. Here are the dataset and tasks used in this work. We use a common public dataset named MIMIC3 and validate our model on two tasks: diagnosis prediction and heart failure prediction. We compare our CGL model with various state-of-the-art baselines, and the model only uses clinical notes. Here are the results of diagnosis and heart failure prediction. The evaluation metrics for diagnosis prediction are weighted F1 score and top key recall. The evaluation metrics for heart failure prediction are AUC and F1. We can see that our CGL model has the best performance. We also demonstrate an ablation study by removing hierarchical embedding, clinical notes, and ontology weights. We said all the removed parts contribute to the prediction performance. We then given an analysis for the prediction of new-onset diseases. We divide the ground truth of diagnosis prediction into two parts: occurred and new onset. Occurred means future diagnoses have occurred in previous visits, while new onset means not. We use CGL without notes in this experiment for a fair comparison with other baselines. We can see that our model is better in both occurred and new onset. It verifies that our proposed collaborative graph learning is able to learn from similar patients and predict new onset diseases in the future. Here are the learned representations of medical codes from GRAM, Timeline, and CGL. The colors represent disease categories in each level. We can see from the figure that representations of timeline is like a random distribution. The representations learned by GRAM have larger intercluster distance and small intracluster distance compared to CGL. We may infer that although higher level diseases of GRAM distribute into multiple clusters, the lower level diseases cannot be well distinguished by GRAM. This figure shows a case study of clinical notes. We try to detect important words related to predictions and unimportant words that has no contributions based on attention weight. The pink color denotes important words and the gray color means unimportant words. We can see that some important words such as acute and respiratory are not detected without penalty. In addition, without penalty, some unimportant words like patient and diagnosis have high attention weight. Therefore, we can conclude that our designed TF-IDF-rectified attention can help to provide interpretability by detecting important words related to predictions. Finally, in this paper, we propose to collaboratively learn representations for patients and diseases by constructing an observation graph and ontology graph. We also designed a TF-IDF-rectified attention method for clinical notes. Detailed analysis are also provided for model predictions. And that's for today's report of our work. Thank you very much for listening.